stress, which is directly proportional to the quadruple of the neutrino temperature. So our first task is to, first of all, is to write down the energy momentum tensor. And so recall that in our convention, the four velocity u mu of a fluid describes the transport of energy, not the transport of particles. And so you can, at first order in perturbation, you can write down this four velocity as follows, where the time component is 1 minus the Newtonian gravitational potential psi, and this comes from the constraint okay, so basically, so if you would go through this, you would get this is a small perturbation, so this is actually second order, so you can just ignore it. So what you have is what is here, and then this is just minus a squared 1 plus 2 psi mu naught squared is minus 1. So this implies that to satisfy this normalization condition, you need to pick up mu naught to be exactly what I wrote here, okay? And then this you don't have to worry too much, because this is the square of this obviously is second order. So what VI is basically it's this coordinate velocity, and at leading order in our at lowest order, it's basically, if you want, a proper peculiar velocity. If we ignore like the perturbation to the metric tensor, then that's just what it is. The physical peculiar velocity of the fluid. And then you can lower the indices, and then you would find that this goes like, then the covariant for vector has those components. Okay? You just lower with the unperturbed metric for this part, obviously. Now, so now we want to write down the neutrino energy momentum tensor, and what we will do is that we will consider actually the mixed form so one index up and one index down, because this basically allows us to reduce the presence of metric fluctuations. What we are really interested in is looking at the fluctuations intrinsic to the fluid and not intrinsic to the metric. Okay, so what you need to do is that you need to start from what we wrote done in the most general possible way. where, remember, so this is the isotropic part of the stress, and this is the anisotropic stress. Okay, and then you just substitute this for velocity, okay, inside this expression, and you find the following. So in Newtonian gauge, obviously, or longitudinal gauge, that we have been using throughout. So the first, the time component is just minus the density, energy density. Then if you calculate the second, Ti naught is minus rho plus P Vi. T naught I is plus rho plus P Vi down. And then the Tij encodes both the isotropic stress and the anisotropic stress. So at this level, you basically have 10 degrees of freedom, and you can also, as we did for the metric, you can do you can decompose them into scalar, vector, and tensor type fluctuations. And we will be, since we only track scalar perturbations, we are only interested in the scalar degrees of freedom. So you can do this scalar vector tensor decomposition. Okay. And the scalar perturbations, so there are the density, the energy density, and the pressure, both of them in the fluid rest frame. Then the curl-free piece of the velocity, which I write V parallel I, as I did before with B, the frame dragging term. And then, what else? There is also a scalar anisotropic stress, which I write, okay, this way. So what we are interested in is this term. What I want to show is that this term is basically, the amplitude of this term is proportional to the quadruple of the, neutrino temperature. And so remember, we defined the perturb distribution function of neutrinos as the following. And the exact same way as we did for the photons, that was for the photons. Okay, that was that's the fractional temperature of the photon distribution. So we interpret this as a fractional perturbation to the effective neutrino temperature, because now at this stage they are collisionless, right? It's after they decoupled from the plasma, as we discussed yesterday, but we assume that they are still relativistic, okay? And we assume that they are still relativistic. So this function n, which describes the perturbation to the neutrino distribution function, in Fourier space, it's also a function of our conformal time, the 3 wave number, and the direction of propagation of the neutrinos. And then basically what you do is, in terms of Boltzmann equation, you do exactly what you did for the photons, okay? You will write down an equation, which is a collisionless Boltzmann equation, and then you do this multiple expansion and you solve, okay? Now what I want to show you is basically that the quadruple, okay, of this perturbation is directly related to this scalar anisotropic stress that shows up in the energy momentum tensor of the neutrinos. And we will see that basically it corresponds to an effective neutrino viscosity with some numerical factor which I want to work out actually. That could also help you reading like more technical papers in the literature. So let me move here. So let's look at this scalar anisotropic stress. So how do we write it down? So we've seen a couple of days ago how to write down a scalar type tensor. And so we do exactly the same because this is a scalar type tensor perturbation. So basically, so we write it as follows. So we construct it out of a scalar function, which by acting on the scalar function with this operator. Okay, and so this is really the scalar, okay, the degree of freedom. 1 degree of freedom, 1 scalar here, okay? Now if I go to Fourier space, Fourier transform this expression. Sorry, here I should specify that it's in terms of in configuration space and then in Fourier space. So because I have two derivatives and I have this complex exponential, this will bring down a factor of e squared, a minus sign, okay? So I will get a minus sign. Then there is a k squared modulus, which I want to take out. And then I have here just the unit vector ki, kj, minus 1/3 delta ij. And then I have the Fourier transform of this function. Okay? And then just for convenience, I want to express this function pi parallel. I will define it as follows. I will define it as 1 over k squared times the average neutrino pressure and times basically another function pi nu of eta k, which, because I took out this factor of 1 over k squared, has basically no dimensions, and we will see that it's basically effectively a viscosity, a shear viscosity. And we will see that it's basically really directly proportional to the quadruple n2, okay? Which also has no dimensions. So in order to do and to check this, what we need is basically a microscopic expression for the energy momentum tensor of the neutrinos. How do I write this energy momentum tensor in terms of the distribution function? So there is a general covariant expression, which I won't discuss. I will just give it. So it is the following. So you have this spin degrees of freedom here. So it's 2 basically, 1 for the left-handed and 1 for the right-handed antineutrino. And then you have to integrate over the momenta. And so there is a measure here where Pi are basically the covariant component of the canonical momentum, which we already computed. Okay? And then you have a factor of the metric to the minus 1/2. And then you have this P mu up, P mu down. So they are the component of the neutrino for momentum. You have to divide by P naught, and you have to then multiply by the distribution function. Okay? And so for neutrinos, we have, okay, for one family of neutrino. Now, as I said, the neutrinos are relativistic. So we have already the expression of the contravariant and covariant canonical momenta. So just to remind you, we found that P naught for relativistic particle is the modulus of the physical momentum divided by A times 1 minus psi at first order in perturbation. So the covariant component is AP 1 plus psi, okay? You just bring the index down with the G naught naught, and then you go to first order, obviously. The Pi is, we found, was P divided by A times 1 plus phi and I, and so the Pi covariant is AP 1 minus phi and I down. Okay? So now the question is, what is the volume measure? Well, now we can basically read it off from here, okay? Because that's what we need. The volume measure so this, it's dp1, dp2, dp3 index down. Okay, so we have, okay, here the expression. So we have an overall a cube, 1 minus 3 phi, and then we multiply the usual three-dimensional volume element, which we would write in spherical coordinate. We write this as p squared dp, and then d omega, well, obviously d omega for, okay, so the two angles that describe the position of the unit vector and at, okay, but I would just drop this. It's obvious to what it should refer, okay? And then we have the 1 over the square root of minus the determinant. And so if you do the calculation for the longitudinal metric, then you get a to the minus 4, 1 minus psi plus 3 phi. Okay? So everything is on the diagonal, so it's very simple. Okay, you just take the product of what you have on the diagonal. For each of these G naught naught, G I, you have a factor of A, and then you have a 1 plus psi, okay, for the G naught naught, and then you have a 1 minus phi for the, a 1 plus 2 psi and 1 minus 2 phi, but you have to take a square root and you have to reverse it, okay? So at the end that brings you to this, okay? And now we are all set. We can start computing. Okay, so let's just practice this once for good. So let's take this expression and compute T naught naught. Okay, let's do it. So For T naught naught, I will have, I leave here the GS, okay? So I have this. I have this factor of the determinant. And so then, okay, I just replace according to the definition. So I have a P naught up, P naught down, P naught up again, and then F, okay? So that's just calculating, okay, this, right? So let's do it. So let's first write down like what we have in the integrand. So we have this. So what is this? So we said this is a cube. So the volume measure is a cube min p squared dp d omega. Then the determinant is a minus 4 1 minus psi plus 3 phi. And then we have the p naught here with a minus sign. Minus ap times 1 plus psi, okay? And then from this I see that, okay, this minus 3 phi plus 3 phi minus psi plus phi, they go away. And then I have factor of a to the 4, a to the minus 4. And so I get at the end something which is fairly simple. There is a minus sign left, and there is an extra p. So minus p cube dp d omega, okay? And so if I put this into the expression of T naught naught, then I get the square root of the spin degeneracy, and then we have simply that. Okay? And then, you know, you do exactly the same for the two others, or the three others. Okay, let me just write down at least two of them. So this, for instance, you will get the following. So you get the following. I insist at first order in perturbation. Because in fact, if you do the calculation, there will be here extra factor of metric fluctuations. However, the function, the distribution function f for the neutrinos, of course, at the homogeneous and isotropic level, it does not depend on n hat, on the direction. So at the homogeneous level, if you integrate, I mean, you get just 0, okay? So you need here to have the perturbed part, okay? So you have already something which is first order in perturbation, which you need in order to get something non-zero. So you basically, at first order in perturbation, you drop the metric fluctuations that are in there, okay? And then if you do the same, for this component, then you get also okay, so no miracle. It looks very much like, you know, what this at this level. Okay, so let's so maybe this I will try to keep somewhere. Just thinking, well, I will come back to this. Let's do this after. So now let's evaluate now this component of the energy momentum tensor. So again, so we have So we have the following. The neutrino distribution function is the unperturbed part minus p df nu bar dp n. Okay, I substitute this into these expressions. And then I look. What do I get? First of all, what do I get at the background level? Let's make sure it's actually consistent with what we expect. So basically at the background level, I would have, okay, the average energy momentum tensor. So this is minus gs 2 pi cube p cube dp d omega f nu bar. Okay, f nu bar does not depend on the angle, so I can just do the integral. So I get minus gs 2 pi squared. I do the integral over the angles, and then I get dp p cube f nu, and this is basically minus, by definition, the energy density, okay, as expected. If I do the calculation for T naught I get 0, as I told you, at the background level, and the same for Ti naught, which I didn't write here. And finally, for the ij piece, then I get gs 2 pi cube so now the integral over the angles, so it's weighted by the component of the unit vector on the sphere. And so if you do it, it's very easy. For instance, you just pick up I and j in the z direction, you will get a mu square, okay, and then you will have to integrate, so there will be, the phi integral will give you a 2 pi, and then the integral over the mu will have this extra factor of mu square inside, so there will be a mu cube divided by 3, okay, and there is a 1/2 in front for the normalization, so that will give you 1/3, okay, so you get 1/3. So you end up with 1/3 of gs, then you're left with a 2 pi square for the momenta, and then that's exactly the same integral as basically the energy density. So it's just 1/3 the energy density, and we know that that's the pressure of a relativistic gas, all right? So all this makes sense. Huh? Okay? So what about the perturbation now? The component of this energy momentum tensor. So let's look at them. Yeah, it's diagonal. Yeah, so you have minus the density and then just the pressure. Ah, sorry, I forgot. Oh, yeah, I forgot. You're right. There is an extra, obviously. Yeah, I took the same, obviously I took z and z, or x or y or y, all right? If you take x or y, or obviously it's 0. Yeah, sorry, yeah, thanks. So there is this here. Yeah, obviously. Thank you. So, yeah, so at the homogeneous and isotropic level, the stress energy tensor is diagonal, all right? Let's just write it now. So it's minus rho p mu, p mu, p mu. Okay? Okay, so what about the perturbations? So for the perturbations, so let's look at let's do two of them. Okay, I will do the naught and the ij. I won't do the I naught. You can do it maybe as an exercise. So we have the following. So the perturbation to the energy momentum tensor then is minus spin degeneracy, tac, dp, p cubed times delta f nu, okay? Now remember, so delta f nu is minus p df nu dpn, where n is not a function of the modulus of the physical momentum, okay? Because all the nodes are affected the same way, in an achromatic way, like the photons in this limit. So we will use actually this to do the integral that we have here. So we start with this. So just substitute this, minus sign will give me a plus sign here. Okay, and then what I need to integrate is this thing. dp, now there is p to the 4, okay, from here, and then there is this term, and then there is n. And the obvious way to go forward is to do an integration by part. So I integrate by part. So let me just take this out. So focus on the momenta. So we have P4, F nu n evaluated, okay, here, and then we have minus integral dp, and so now we have F nu, and then we need to take the derivative of P4n. So first of all, what is here? So at infinity it's 0, obviously, right? There is the one, that's the Fermi-Dirac distribution. So in the limit p goes to infinity, that's just exponentially suppressed. And then in the limit p goes to 0, if you do the development, well, you will see that, so that just goes to 1, right? The limit of very small momenta, there is the 1 over exponential plus 1. So it just goes to 0 because of the P4. So it's 0. Okay, this is 0. And then, obviously, here what we use the fact that n does not depend on the modulus of the physical momentum. So this is basically just 4 times p to the cube times n. Okay? So we bring again a minus sign in front. GS, 2 pi cube. And then we have integral. So let's just write this down. dp p cube. And then I have 4 times f nu bar times n. Okay? And now what I will do is that I will do the integral over the angles. And the only angle dependence here is in n. So this, okay, you see, this will just give me, well, the monopole, and not, okay, by definition. Obviously, I need to remove a factor of 1 over 4 pi, okay, to do the average. Okay, so I'm left with minus, let's keep track of this, gs 2 pi squared. I have the monopole for and not okay. And now so this monopole is only a function of time and space, so I can just take it out of this integral. Okay? It's not a function of the modulus of the physical momentum. Remember? And is not a function. Okay? It was only a function of the position on the sky. No, the n naught now, the n naught does not depend. The n does not depend on p. And I only have an integral to d over p. All right? So I can just take it out of this integral. Well, in principle, it's a function of time and space. What I did is only the angular averaging, right? But the angular averaging could give me a different answer depending on where I do it in the fluid. The monopole could change, okay? Okay, so it's a function of time and space, but not a function of the physical momentum. Okay, so I take it out, and so I get minus n naught times 4 times an integral which I recognize is just the average energy density. Okay, so it's just minus 4. Okay, that's what it is. And so there is a 4 because n naught, I tell you, it's like effectively it's like a fractional perturbation to the neutrino temperature. And since the energy density goes like T to the 4, then obviously to have the perturbation to the energy density, you need to take 4 times the perturbation to the temperature. So what we really have here is really the perturbation to the neutrino energy density. That makes sense, okay? So let's do so you do the same for the knot I, and now we'll do the ij, okay, which is the component which is relevant to the anisotropic stress. So we have so let's start again. So we have this d omega dp p cube n I n j minus p okay, so we'll do the same. So let me see if I did already some simplifications here. Yeah, so I do the first steps, they are the same. Okay, I start first of all I start with the integral over the momenta. Okay, so again integration by part, I kill the term, the boundary term, I kill it, I get a minus sign, then left, and then I get only to take the derivative of the p to the 4. So I get a 4p cubed, so basically at this stage you are here. Let's write this down. Okay, and let's put it like that. So I will put now the n here, because the n does not depend on the modulus anymore. It does not depend on the modulus. And we have this, okay, left here. Okay. So there will be something here that will give me 4 times the average energy density, provided that I take a factor of 1 over 2 pi squared, okay? So there is an extra factor of 1 over 4 pi, of course, which I put with this integral, this angular averaging, okay? Times 1 over 4 pi. Okay? So what we need to evaluate is, okay, is this. So there are various ways you can evaluate this. I will do it in a certain way. And the plan is, first of all, to go to Fourier space. Now, at this stage, it's time to go to Fourier space. Okay, so I will take delta Ti j, which is a function of eta and x, and I go to function of eta and k. Okay, I will do the same for n. There, it's a function of eta x and n at, and it becomes a function of eta k and n at. Okay. And now I will consider two, what I will do is that I will contract the left-hand side with products of the unit vector k hat. So let's consider two possibilities. The idea is just to get a scalar that we understand what to do with. So I will multiply now the left-hand side, so it's all in Fourier space, okay, by this. Yeah? So what do I get? So I get 4 rho bar, 1 over 4 pi, integral over the angles, and then, okay, I have two products of n, and you see I get basically a scalar product between k hat and n squared, okay? The square of this scalar product times n k hat, okay? So first of all, now I can pick up my angles as follows. So there will be mu, that will be the cosine between these two angles, and then there is the phi, the azimuthal angle, which I immediately integrate over, right? Get the 2 pi. And so this becomes 4 rho bar times 1 over 2. Then I need to do this integral. And now it's very easy to proceed because we did the same basically with the photons, right? And I wrote down the same expression. I told you how the multiple moments are defined, right? They are integrals of, they were defined as integrals of the photon temperature perturbation times the Legendre polynomial. So the only thing you need to do is just write mu squared down in terms of Legendre polynomial. So obviously here you need 2, okay? You need the 0 and the second. Okay, the second is 1 over 2 times 3 mu squared minus 1, and then you need to add an extra constant piece to get the mu squared. And then you trivially get 4 pi, 4 rho nu bar, so there will be a factor of 1 over 3 times the monopole minus 2/5 the quadruple, where by definition, maybe I should write down this definition again. So the definition is, I'm just trying to remember what was the definition of these multiples. Well, it's in, you take it, it's in the, it's, I don't remember it, but PL of mu, I think this is just the definition. Okay, with the understanding that the integral over the azimuthal angle is trivial, okay? Okay, first thing, so we get to a first expression, which is the following. So this contraction, let's write it down here, gives me this. And then obviously there is a second contraction which we can compute, which is basically the trace, okay? So then we look at this. So what is this? Well, it's 4 rho bar nu. So again, same story. So there is a 2 pi squared that goes away. So there is this 1 over 4 pi left. The integral over the sphere. And then now it's basically contracting here just gives me 1, right? Because n hat is normalized to unity. So that's just trivially 1 times n. And that for sure we need to know, we know how to do quickly, right? We get back the monopole, right? Up to some, actually, there is no factor. So it's just for average energy density times the monopole, okay? Nice, but what do I do with this? Why is this useful? So it's useful for the following reason, because now I'm asking how shall I write down these Fourier modes of the perturbation to the energy momentum tensor. You see there are two indices. There are indices, spatial indices, and this is a function of eta and one vector, okay? So the only possibility is that this generically will be expressed as either, you have two possibilities. Either there is a term that multiplies the Kronecker symbol, okay, for your two indices. So let's write it this. There is some function of eta and k modulus that multiplies the Kronecker symbols. Or the second option is that you basically have a tensor product of components of k in the dependence, okay? I would say generically, at least that's what I would expect. So now I can use what I did, okay, at this level. So let me now, I want to organize this slightly differently, because now I want to have basically the scalar anisotropic stress appear, okay? So what I will do is that I will move some of this on that side, okay? In order to have a term that is k hat minus 1/3 of delta ij, okay, which is the term I'm looking for. And then I will just relabel this function as follows. So I do this move around, and I claim then that what I will have is I will have a perturbation to the isotropic pressure multiplying this Kronecker symbol, so on the diagonal, and then I have this basically anisotropic stress multiplying okay, this term. So if I would go back in configuration space, this would be exactly this pi parallel ij. Okay? So let's check what we get. No, where do we have to go? I have to go here. So now I use these two contractions. So I start from this. Okay, so I will take now, I take this expression and I will contract it on the left-hand side. Okay, I will take the trace. Okay, and then what do I find? Because this is anisotropic, that gives that zero trace. Okay, so the only contribution I get is the contribution from the isotropic pressure. But I take the trace, so there is a factor of 3, okay? 3 delta P nu. And I know that this should be equal to, because I did the calculation, 4 rho bar naught, okay? What does this mean? It means then that delta P nu is 4/3. And it's just, I can write it this way, it's 1/3 times 4 n naught, and 1/3 of the energy density, but that's just the homogeneous pressure times 4 n naught. But there is a 4 here again because n naught is a fractional perturbation to the temperature and not the energy density. So all this makes sense, okay? That's exactly what I was expecting, and I recover this is really the perturbation to the isotropic pressure. And so then we look at now we just have to look at this piece. Okay, so I do this contraction here and there, and so that will pick up the term, the anisotropic stress. And so if you do it, you get delta P nu, okay, obviously, because that will just give me 1. And then here you have to be a bit careful, so you get minus P bar pi nu, and so the first term will give you 1, and then you have a minus 1/3, okay? So you have this 2/3. And then you did the calculation, we did the calculation, and that's what we want, that's what we find, okay? A chi? Yeah, k is unit vector. It's okay? And so what do I get? So I get, sorry, so this I know it's from here. It's 4 n naught P nu bar. And then let me replace this, yes. And here I can also replace, I know that, so what did I do here? Nothing. I didn't do anything at this stage. And now I bring this result here, okay? So I get 1/3 of, so this 1/3 of rho bar is obviously the P bar, okay, which is here, so that matches what I have here. And then what is left has to be equal to, here has to be equal to what is, to the second term, which is minus 4/3. So there is a 4, then there is a 1/3 again of the energy density, so it's P bar, and then I have 2/5 of N2, okay? And so this with this together tells me that so this tells me that no, that's what I'm looking for, right? So now this effective neutrino viscosity is just directly proportional to the quadrupole. And if I put here the numbers, I get 12 over 5, okay, times the quadrupole. Okay, so at the level of the energy momentum tensor, what I have is like I have an imperfect fluid. There is a shear stress, okay, and one of the terms there in the shear stress is basically it's a viscosity, all right? And this viscosity, I mean here, if you want, it's a function of space and time, and it's directly proportional to the local quadrupole of the neutrino density distribution. Okay, and so I wanted to point out, because if you open technical papers, like if you open Fujiyama or Mein-Bertschinger, maybe, or these papers, then you will see this. I think this factor appears. So I just wanted to show you where does it come from? How do you get it? Okay. So maybe we have just 5 minutes break and then we convene. Yeah, again. Those have decoupled from the plasma at 1.4 MeV. They are essentially collisionless. And so, unlike photons, no sound waves can propagate in the neutrino component, but so there is no sound horizon, etc. But nevertheless, you can define the characteristic scale over which the neutrino propagate, and this scale is known as the freestreaming length, and it's defined in analogy with the Jeans length that you would have in a collisional fluid, obviously. So let's just go again briefly through the Jeans length. So what is the Jeans length? So you have basically you have a fluid, okay, a gas, and self-gravitating with non-zero pressure. And you basically the Jeans length is the scale at which pressure gradients basically balance the pull of gravity. So how do you get this scale? You basically equate two characteristic time scale, one related to the pressure and one related to gravity. And so these two characteristic time scales. So let's just write down the Jeans length, lambda j. And so you basically equate, first of all, the sound crossing time. So what is the sound crossing time? So imagine that you have a perturbation of size L. Okay, physical size L. Then the sound crossing time is the time that it would take to basically a sound wave, okay, in the fluid to propagate from one side to the other side of the perturbation. Okay? So it's basically the time it takes to propagate information about disturbances in the distribution. So it's basically the length of the perturbation divided by the sound speed. And then there is a second scale which is related to gravity, which is the free fall time. Okay, if I have like a small perturbation in the energy density, okay, let's say a top hat perturbation, how much time does it take for it to basically to feel that it's, you know, its own gravity and collapse? Well, that's the free fall time. So it will collapse on the free fall time. And so this free fall time is up to factors of unity, which I don't put. It's basically 1 over g times rho. Okay, so it's, of course, it's inversely proportional to the gravitational coupling and to the density. Okay, naively, that makes sense. So then, the Jeans length, basically, you obtain it by equating these two time scales. So if you have a very small perturbation, the following will happen. If you have a perturbation whose size is smaller than the Jeans scale, this perturbation will be stable to its own gravity because the sound crossing time will be very short, shorter than the free fall time. So whenever there is a disturbance at this level, okay, in the density, the pressure can restore equilibrium. On the contrary, if you have perturbations with a wavelength larger than the Jeans scale, then you're unstable because it would take too much time for sound waves to propagate from one side to the other side of the perturbation compared to the free fall time. Okay, so perturbation with a wavelength larger than the Jeans scales, they are unstable, and perturbations smaller than the Jeans scale are stable. And so the Jeans scale, you obtain it by equating these two characteristic time scales, and so you see immediately that they are equal when L is equal to, by definition, the Jeans length, and this is CS divided by 0. And so then you can define a Jeans wave number, which is basically, it will be 2 pi over lambda j, but let's forget about the 2 pi, okay, at the moment. And so that would go like square root of g rho divided by CS. Okay, or equivalently g squared is g rho divided by CS squared. So now we basically do the same for neutrinos. We will define a characteristic, if you want, Jeans scale, but that we call free streaming because there are no collisions, right? So free streaming length, free streaming, and so we call it lambda fs, and here I will define lambda as the physical, okay, not the co-moving. So I will write it now down a bit more carefully. So because I want to write it down as a function of the Jeans, the free streaming wave number. So I will put 1 over the free streaming wave number, but this will be co-moving. This is physical, and lambda fs is physical, kfs will be co-moving. Okay, sorry for the So I need to put a factor of a scale factor up there, okay? And to get a physical wave number, okay? And then in analogy with what we have, basically, we defined, so I do this here. So the KFS squared, which is generically a function of time, so is defined as, so there will be a G rho, now an extra factor of, okay, G rho bar, okay, because we are, I mean, density fluctuations are, the density is fairly homogeneous, okay, in the early universe. And then we need to put this factor of A squared, because again, it's co-moving. And we divide, instead of dividing by a sound speed square, we divide by basically a characteristic neutrino velocity dispersion squared. No, not squared, neutrino velocity dispersion. Okay? And so we have the same scaling, G rho divided by some typical velocity squared. So let's consider two limits. First of all, neutrinos are relativistic. So temperature T of the neutrino is much larger than the neutrino mass. So in this case, basically they propagate at the speed of light, essentially, right? Close to the speed of light, okay? So sigma V here, you take it as being basically unity approximately. And so then you get the following scaling. So from this, you read off that now because rho, so let me see, I didn't do this part actually. Actually, it would be useful to do one more step here, to use the fact that basically rho bar is, I assume that I have an Einstein de Sitter universe, okay, so rho bar is basically the critical density approximately, and so what do I want to do? 3h squared divided by 8 pi g here, okay? And so I get 3/2 of a squared h squared divided by sigma v squared, and which I can write also as 3/2 of a times h is the co-moving Abel rate divided by sigma v square, okay? Sorry for that. Okay, so the scaling is a squared, h squared divided by velocity dispersion squared. So when sigma v is over the unity, then I read off from here that KFS goes like AH, or goes like this co-moving Abel rate. So that implies that the physical freestreaming scale goes like A divided by KFS. And so it goes like h to the -1, and h goes 1 over t, so it goes like t. So it grows linearly with the time. Okay? So now what happened in the other limit when the neutrinos are non-relativistic? Well, then you need to estimate their velocity dispersion. And so it's basically, you calculate the average of their physical momentum squared, okay? Remember, always using the decoupled from the plasma, they become non-relativistic, but remember the collisionless-Liouville equation. Nevertheless, you need to use the relativistic Fermi-Dirac expression in this calculation. And you get something of order 3.6 times 10 to the -7 times 1 electron volt m nu squared 1 over A squared. So basically, redshift of momenta, sigma V goes like 1 over A. So this happens after once they become non-relativistic. So that would be basically for scale factor smaller than the scale factor at which they become non-relativistic, and this is for A greater than A n r. I'm writing this because I will try to draw a plot. It will be the second figure you will see in this, this course. Okay, so in this case, what do we get? How does KFS scale? So KFS now will go, so there is a 1 over A, okay, coming from sigma V, so it goes like, KFS goes like A squared H, which implies that lambda Fs goes like 1 over AH, and this is T to the 1/3. I'm assuming matter domination, okay? Because anyway, this for realistic neutrino masses, I mean, this transition happens in matter domination, deep in matter domination, okay? So it's always matter domination scale factor. And so what you see here is that the physical scale grows like T to the 1/3. I mean, slower than the scale factor. What does this mean? Well, this means that basically the co-moving wave number, the co-moving free-streaming wave number will reach basically a minimum at the non-relativistic transition. And so this minimum value, I will write it KNR, which is KFS at ANR. Let me give it to you. It's approximately the following, 0.018 omega m1/2 H MPC minus 1. So it's basically, you see, it's somewhat larger scale than the K equivalence, which is about the 0.2, basically, approximately. And so it's on fairly large scales. So let me try to sketch this now in a figure. Oops. So what do I want to show in this figure? I want to show co-moving wave numbers. In unit of age inverse megaparsec. And here I will put the scale factor. Okay? All matter domination, and in the middle here I will put the scale factor at which the non-relativistic transition happens. Do I have a... Yeah, so just to give you an idea, if you take a neutrino mass, well, it's a sum actually of neutrino masses of order 0.1 electron volt, then the relativistic to non-relativistic transition happens at approximately, I found 5.3 times 10 to the minus 3. Okay? So somewhat, redshift of approximately 200 or so, something like that. Okay, so now what do we want to show here? First of all, I want to show what the co-moving Hubble rate is doing. So in matter domination, the co-moving Hubble rate, so let's do this here. So the co-moving Hubble rate so it goes like, so h goes like a to the 1 over the time, a goes like t to the 2/3, so this goes like t to the minus 1/3, so it goes like 1 over the square root of a. Huh? Okay? So as A increases, it becomes the co-moving wave number becomes smaller. Obviously, it's basically the distance over which you can exchange information at a given time, and so it grows with the expansion of the universe. So it's doing something like that as some square root, right? So it's going to be hard, but let's just do. Okay. That's what it does. Okay. And now what's going on with the free streaming? So the free streaming we know. So initially it goes like, where do you write the, so initially it goes also as edge, curly edge, when the neutrinos are relativistic. So it also scales as a to the minus 1/2, okay? Prior to the non-relativistic transition, so it would be here. Some factor of unity, okay, it's basically there. So actually if you do a detailed calculation and definition, it's obviously slightly larger than this distance over which you can basically propagate information at the speed of light. And then here, so it changes, here its behavior changes to, so what did we say? So we had when it's non-relativistic, but I erased that, unfortunately, so I need to figure this out again. So we had that KFS, we say it's going like a squared h, so it's going to go 1/3, so it's the opposite. It goes like t to the 1/3, so it goes like a to the square root, and not 1 over square root of a, okay? 4/3 and 1 over t. So it grows again. Okay, so here it goes like KFS, here goes like a to the 1/2. Okay, well, okay, it does this. So basically what does this mean? This means that the free streaming scale, basically the configuration space, the free streaming length basically drops. Okay, and the reason is that because the neutrino becomes suddenly non-relativistic, they propagate at a much lower speed than the speed of light, and so I know they travel a distance which is shorter, and so as a consequence, the co-moving wave number basically increases as follows. Okay, so now what would happen to perturbations? So basically, if you look first of all at So let me just now just put some scale here. So here you would have something like 10 to the minus 2 for, say, realistic value of the neutrino mass, okay? Let's say over the 0.1 EV, 0.2. This you would have here 10 to the minus 3 co-moving wave number. Something like that. So first of all, if you look at the lower part of this figure, so all what is, okay, this is the minimum. This is the minimum free streaming wave number. Okay, so for perturbations in the neutrino density, which have a wave number, co-moving wave number smaller than KNR, basically they are never affected by free streaming. So here, so long as they are super horizons, so long as their wave number k its co-moving is smaller than, is bigger, so long as the 1 over k is smaller than curly edge, they are frozen. Okay, and they basically, they just trace metric fluctuation. And then once they enter here, they just behave as cold dark matter. Because their wave number is always larger than the free-streaming scale. Okay? So we're talking about perturbations with a wavelength much larger than the free-streaming scale, so it behaves essentially as cold dark matter. Okay? It's insensitive to the fact that, neutrinos are, have a non-zero velocity dispersion. Okay? So here it would behave like cold dark matter. For the neutrino density perturbation, which have a wave number actually larger than kNr, then something else happens, because once they enter the horizon, then they are strongly affected by free streaming. And so basically they are damped very quickly by free streaming, and the effect obviously is stronger as their wave number is larger. Okay? So basically what this does is that if you want at the level of the distribution, what this does is that you create a quadrupole, and then this quadrupole in the neutrino distribution function propagates into all the higher multipoles, and then you basically transfer all what you have in the low multipoles to the high multipoles, and then you damped basically the density perturbation. So the density perturbation in the neutrino component at small scales are very quickly damped. And it's only when you exit here again that then you can grow again and try to catch what's going on in the CDM plus baryon component. Okay? So the bottom line is that there is a characteristic free streaming scale above which neutrino perturbation essentially behave as cold dark matter, and below which, I'm talking configuration space, density fluctuations are damped. Okay? So what's the impact of this free streaming on the growth of cold dark matter fluctuation? Well, this free streaming has an impact because obviously neutrino, any component of the universe contributes to the gravitational potential. So if a neutrino can free stream out of perturbations, basically they will reduce, if you want, the gravitational pull that is felt by cold dark matter, for instance. So the free streaming of neutrinos, as a consequence, will reduce the growth of cold dark matter perturbations on scale, configuration, on length, less than the free streaming length. Okay, so let's look at this now briefly. So once the neutrino become non-relativistic, you can basically use a fluid approximation, because the speed of the neutrinos becomes much smaller than unity. So the higher order moments of the distribution function are strongly suppressed relative to basically the energy density and the average bulk velocity. So you can use a fluid approximation. With the exception that basically the free streaming basically plays the role of an effective pressure. And then you can combine the neutrinos. Okay, so the fluid approximation for neutrinos with basically the Also fluid approximation for cold dark matter, because for the exact same reason, cold dark matter, okay, it's not obviously it's not a fluid, but in the non-relativistic, because it's non-relativistic, the higher moments of the distribution function are strongly suppressed. You take moments, you multiply by powers of the typical momentum that is suppressed, or velocity, and so you can basically describe cold dark matter very well with the usual continuity and momentum conservation equation. Okay, and same for neutrinos. And obviously, these two, you ignore baryons, and you can also safely ignore photons, because in matter domination they are relevant. You ignore the baryons, let's just all put them as cold dark matter. We ignore the fact that baryons have effectively a real pressure. And then we can combine, basically, the continuity momentum conservation for the neutrinos, continuity momentum conservation for cold dark matter, into two second order equations. Let me just write them down, and then I will explain just what they are. Okay, in two equations of this form. So what did I do? I started basically from so I started from the following. So I have the cold dark matter, density perturbation, and in principle I also have, for instance, I could use the divergence of the cold dark matter peculiar velocity. Let's put it VC, okay? And the same for neutrinos in this effective fluid description. Okay, there will be some bulk velocity. I get momentum continuity and momentum conservation equations. And you can massage them and basically combine for each species these two equations into a single second order equation for the density fluctuation. So that's what I did here. That's what you would get for cold dark matter, and that's what you get for the neutrinos. What you have on the right-hand side is basically the following. There is first of all one term which is the same, which is the gravitational pull, okay, which everybody feels democratically. So it's basically, in the non-relativistic limit, you have the usual Poisson equation, which is sourced by fluctuation, by density of the density of in the cold dark matter and the density in the neutrinos. And now what I did here is that I basically split the contribution into so let me write this here. I defined now F nu is basically the fractional contribution, okay, of the neutrinos to the non-relativistic dust. Fc is that of cold dark matter, and I have, of course, F nu plus Fc is 1, okay? And everything behaves the same, right? The energy density at this level goes like a to the minus 3 in both cases, because everything is non-relativistic. Okay, so basically what you would have, you would have like a Poisson equation of some, okay, like this. So if this is co-moving, then you have 4 pi g rho times a squared, and then in the rho, you have the contribution from the cold dark matter and from the neutrinos weighted by the appropriate mass fractions, okay? And then on top of this, in the equation for the neutrinos, well, you have this extra pressure effect, okay, which appears through this term. Okay, where the characteristic scale is the Freestreaming scale. Okay, so that would be your pressure gradient. And obviously all this is written in Fourier space. So I'm looking now at the Fourier evolution. In configuration space, you would have pressure gradients, okay, effectively. Okay. So now, basically, what I'm interested in these last minutes, I just want to discuss this piece. Okay, that's basically, that's the linear growth equation for cold dark matter density perturbation in the presence of neutrinos. Okay, so you see that neutrino will affect the growth of cold dark matter density fluctuations because they contribute to the gravitational pull. Okay? So the question is now, how does the free streaming of neutrinos affect the growth of cold dark matter fluctuations? Also maybe, so the dot, by the way, they mean derivative relative to conformal time. I should also tell you that. H is the co-moving Hubble rate. Okay, what else do I need to see? And these variables are in Fourier space. Okay, so I have, for instance, delta C is delta C of eta and k, right? Okay? But because the Fourier modes involve independently, I mean, as you can see, for cold dark matter, there is absolutely no k dependence. But nevertheless, there will be, I mean, the result will depend on k, basically because of the neutrinos. And so if I consider, so you can do the following. First of all, you can just do a change of you can change the time coordinate. From the conformal time, you introduce a new time variable which I called y, which is the ln of a divided by a and r. So if you do that, the linear growth equation for cold dark matter perturbation takes the following form. A prime is a derivative with respect to y. So it takes this simple form, 1/2 of dc prime is 3/2 of fc dc plus. Okay, that's it. And all this assumes, again, matter domination and basically Einstein de Sitter. Okay, I'm assuming to do that, I'm assuming Einstein de Sitter. And now we can solve it easily, okay, in two different limits. First of all, we assume, let's assume that the wavelength or the wave number k is much smaller than basically the typical free streaming scale. In this limit, I told you in this limit basically you're down here. Neutrino density perturbations, they behave like cold dark matter. Okay, so basically what I can do here, I can replace delta nu by delta c. They are the same. Okay, so then all this, okay, sums to 3/2 of delta c. Right? So then you get the following equation, and then you try the solution of the form e to the ry, and you will find an equation for r, which is basically, which gives you two solutions, and they are the following. Well, can I write this down here, maybe? You get r plus minus. So you have to solve the characteristic. Let me just write down the characteristic equation. It's r squared plus 1/2 r minus 3/2 equals 0. Okay, with this trial solution. Okay, and which you trivially solve as r plus minus. You have 1 and minus 3/2. So you recover. So this tells you that there is a growing mode going like e to the y, and y is the ln of a, so it's just going as a. It's the usual, okay, the usual growing mode in Einstein de Sitter. And this is the decaying mode. Okay? Now, if you look now at wave numbers which are much bigger or bigger than the characteristic free streaming scale, obviously this is all these differential equations that have time-dependent coefficients. You cannot just solve them this way, right? You need to solve them numerically. Or I'm just giving you intuitively what's going on. Okay. So in the other limit, where k is much bigger than the characteristic free streaming wave number, then what do we do with this? We set it to 0. Because I told you the neutrino density fluctuations are damped by the free streaming. They are essentially 0. Right? So I ignore, in the limit actually where k goes to infinity, this is the limit. This goes to 0 in the limit k goes to infinity. Okay? So I ignore this term. So I get now an equation which is slightly different from the first we saw, because it has this extra okay, FC term. I mean, basically, the gravitational pull is only given by the cold dark matter. The neutrinos, they have basically streamed out of the fluctuation because the fluctuation is too small. Okay? And so if you solve it now using the same method, then that's what you find. So we'll find that r plus minus is 1/4 of minus 1 plus minus 25. And then if you express Fc as 1 minus F nu, then you will write this down as 25 minus 24 F nu. And if you look at the growing mode solution and you assume F nu small, then you get 1, but there is a minus 3/5 of F nu. And realistically, F nu is small, so that's a very good approximation. So you see now that the growing mode, the growth cold dark matter is suppressed at small scales because of the neutrino free streaming. I think that's only, actually, it's perfect. So I guess got what I wanted to say. Okay, so this will have, this has an impact because this will affect basically the growth of cold dark matter fluctuations, okay, the large scale structure, the formation of halos. So that's basically the last thing I will discuss tomorrow. So what I plan to do tomorrow is to move to large scale structure, discuss some analytic approximations to, to the clustering of dark matter halos, and then briefly comment about, what's the effect of these massive neutrinos on the large scale structure, and maybe how we could, we hope to detect them. Okay. So, thank you.